Okay, so I welcome you again for the second part of the chapter 4, that is 8th lecture for this course. And as I mentioned during the lecture 7, that this chapter 4 is divided in two component, which is on seismic hazard analysis. So we already discussed partly, now we continue with that. So again we have covered already 4 topics and we are under fourth topic, seismic hazard analysis, the second part of that. So this is chapter 4. Now before I go ahead, let us that recap from the lecture 7. In the lecture 7 we have covered these components, seismic hazard analysis, which is DSHA and PSHA. And before I talk lecture 7, 8th today, so let me that is what are the topics for this lecture. For earthquake source characterization, spatial uncertainty, size uncertainty, Gutenberg-Richter recurrence law, temporal uncertainty. So we are going to talk this lecture under these 5 topics. And let me acknowledge that most of the information which is taken in this lecture for these topics are from the textbook of Kramer, but I will explain each and everything. So that is going to be very different than what you have only in the textbook. So first thing is, we continue with PSHA. In PSHA, this lecture is on probability and uncertainty and other things. So this is basically based on PSHA. We already discussed DSHA and PSHA in the last lecture. In case of PSHA, uncertainties are there. So this lecture is adding to PSHA. So probabilistic seismic hazard analysis, that is PSHA, allows uncertainties in the size, location, rate of occurrence and effects of earthquakes to be explicitly considered in the evaluation of seismic hazards. So that is here that we can consider these uncertainty while dealing with the seismic hazard. A PSHA requires that uncertainties in earthquake location, size, recurrence and ground shaking effects be quantified. So we need to quantify those effects. Now when we want to quantify this, so in the earthquake source characterization, this require consideration of spatial characteristics of the source, distribution of earthquakes within that source, distribution of earthquake size for each source, distribution of earthquake with time. So these uncertainty may be related to these issues, and each of these characteristics involves some degree of above characteristics. So we will be dealing with the uncertainties related to these issues one by one. Now let us first consider 3 types of uncertainties. First is what we call spatial uncertainty. Spatial word is here, it is very different than what we have spatial. So here you have spatial and this is not the spatial, there is another word SP is spatial, and this is kind of an particular. So this is not the spatial, this spatial is here related to space. That is the uncertainty which is related to space or distance. Then you have size uncertainty, then you have temporal. Temporal here is not temporary, again this is related to time. Temporal word in use in the earthquake engineering related to time. So and size is normally related to magnitude. So let us talk about the uncertainty which is related to space. The geometries of earthquake sources depend on the tectonic processes involved in their formulation. So how they are created, the sources are created. So that will depend on. Earthquake associated with volcanic activity, normally they are originate in zones near the volcanoes which are small enough to allow to be characterized as point sources. So if you have the small, then you can consider as a point sources. if you have well defined fault planes on which earthquake can occur at many different locations, they can be considered as a two dimensional sources. Now for example, these are the, this slide is giving you the examples, and this is again, these figures are taken from the Kramer. So examples of different source zone geometries, first one is short fault that can be modeled as a point source. So you have a like a line, it is fault, maybe fault line, and this is your site. So you are considering that this is like as a point source. So it is one dimensional case. Then you have a plane case, shallow fault model linear source. So you have a 2D case and your site is here. So source to site linear variation. But the third one is 3 dimensional source zone, where you have from the source to site, like for example this is a kind of source. So all the 4 corners are will kind of link with the site. So this is in 3 dimensional case. So the spatial uncertainty can be deals. Naturally the first one is the simplest, third one is the most complicated, which is in 3D case, which require more. So this spatial uncertainty can be dealt like this. Earthquakes are usually assumed to be uniformly distributed within a particular source zone. That is, earthquakes are considered equally likely to occur at any location. So within the same source zone, you have, let us say this is same source zone, you have a number of earthquakes, which may be like here in the PSHA, we do not only consider one earthquake, due to a source or due to a fault line there may be a number of earthquakes. Now within that what are the chances of occurring, whether this small earthquake will occur, large earthquake will occur? No, we consider normally the uniformly uniformly distributed. However, this assumption of uniformly is required in the sense, even if you consider non-uniform distribution, in that case it need to be justified with some information. There should be sufficient information that we are not considering uniform distribution, rather than we are considering non-uniform distribution. So if you do not have any particular information data, then we consider the uniform distribution. Continue with spatial uncertainty. A uniform distribution within the source zone does not often translate into uniform distribution of source to site distance. Even we consider that our sources are uniform, the effect is similar, but still it will not lead to us to uniform distribution of source to site distance, because the distances may not be the same. So it will not be uniform distribution of source to site distance. And as we mentioned in the last lecture, we use a predictive relationship, which is recurrence relationship, which is express ground motion parameters in terms of some measure of source to site distance. The spatial uncertainty must be described with respect to the appropriate distance parameters. So you have this spatial uncertainty, and naturally this will involve a distance parameter, because it is related to space. So a distance parameter will be involved in this case. The uncertainty in source to site distance can be described by a probability density function, and this probability density function, sometime it is called in short PDF, probability density function. So that is there. Continue with this. Now the second uncertainty, first one was related to the spatial uncertainty related to space. Now the second one is related to size of earthquake, size uncertainty. Once an earthquake source is identified and its corresponding source zone characterized, the attention is required towards evaluation of the sizes of earthquake that the source zone can be expected to produce. Like now we will talk about size of the earthquake, and with the size of earthquakes that is expected to be reproduced at that site. All source zones have a maximum earthquake magnitude that cannot be exceeded. Yeah, this is very important here. It can be large for some and small for. So what we do, you have a different, like let us say you have a site, and let us say 3 faults are nearby which will influence the site. So each fault, or it is creating a number of earthquakes. Now you decide that this is the maximum value of earthquake magnitude which is expected from this fault, and naturally when the next coming from the same source, that will not be exceeded. So, this maximum earthquake magnitude is decided, otherwise if we keep it increasing, it will be too much conservative approach, and then it will be very difficult to design structures. So, there we need to decide, we need to put a cap that this is the maximum earthquake magnitude considered for a particular source zone. Then continue with the size uncertainty. In general, the source zone will produce earthquakes of different sizes as up to the maximum earthquake, with smaller earthquake occurring more frequently than the larger ones. So, you may be perhaps knowing that the chances of occurring smaller earthquakes is higher than the bigger or large earthquakes, and the strain energy may be released or in the form of earthquakes, assuming that all strain energy is released by earthquake of magnitude 5.5 to 9, and that average fault displacement is 1/2 of the maximum surface displacement. So, with this data, if we consider between magnitude 5.5 to 9, then average fault displacement will be approximately half of the maximum surface displacement. Now, continue with this on the side uncertainty. This graph shows for different magnitudes return periods in the year, and this return period has been found out for different slip rate. So, here you have 10 centimeter per year, 1 centimeter, 0.1 centimeter, so on. So, when the rate of slip is higher, then return period for the same magnitude is very low. That means, for example, 8 magnitude earthquake, it is less than 100 years. But when the rate of your slip rate decreases, then return period required is high. That means, return period is a period after which a particular magnitude earthquake is expected to repeat. So, it is repeat. So, naturally one thing is sure, it is as we just discussed that the chances return period will be low for low magnitude earthquakes. For example, 6, 7 magnitude earthquakes have a smaller return period than 8 and 9. So, when you increase the magnitude of earthquake, the return period is going to increase, and at the same time if you decrease the rate of strain, slip rate of strain, the return period will increase. Continue with the size uncertainty. The distribution of earthquake sizes in a given period of time is described by what is called recurrence law. A basic, this will be with respect to recurrence law, and basic assumption of PSHA is that the recurrence law obtained from past seismicity is appropriate for the prediction of future seismicity. So, this is one of the important, like what are the we have data from the past seismicity, and we prepare based on those data some relationship for recurrence law, and then we suggest that this is expected to be followed in the future also. So, this is the best way, like we analyze the data of the past earthquakes, and then on the basis of it we decide about the recurrence law. The Gutenberg-Richter recurrence law, which assumes an exponential distribution of magnitude, is commonly used with modification to account for minimum and maximum magnitude. So, this Gutenberg-Richter recurrence law we are going to discuss in detail in the next slides. So, this Gutenberg-Richter recurrence law we will call it in short GRR law. So, wherever rather than repeating this word Gutenberg-Richter recurrence, GRR will stand for Gutenberg-Richter recurrence. So, these researchers Gutenberg and Richter in 1944 gathered data for the Southern California earthquakes over a period of many years and organized the data according to the number of earthquakes that exceeded different magnitudes during that time period. So, what they have done? They have collected data of past earthquake for many years, for decades. Those data are available, and then they said, let us say magnitude 5, 6, 7 or like this one, how many numbers of earthquake exceed more than 7, how many numbers exceed more than 6. Of course, when you say more than 6, already which are exceeding more than 7 will be also included in 6, and how many exceeded more than 5, so that will be there. So, that means you categorize in different, like what are the chances of occurrence of an earthquake higher than a given magnitude. They divided the number of accidents of each magnitude by the length of the time period, define a mean annual rate of accidents lambda m of an earthquake of magnitude m. So, this is important. What is the magnitude? Is m, that is the threshold value, and mean annual rate of accidents lambda m. Lambda m shows the rate of accidents and in a year, that means how many times in a year you expect that this earthquake will come more than that given magnitude. So, naturally this annual rate of accidents is expected to be higher for the lower magnitude earthquakes. If your magnitude is small, then chances are more that in a year you will get more accidents. But if your magnitude is very high, so it may be even 0. Suppose if I say 8 magnitude earthquake, it is it may occur only very in few many number of years rather than every year. So, continue with this GRR law, the mean annual rate of accidents is greater than the large earthquakes, which we already discussed. The reciprocal of this annual rate of accidents for a particular magnitude is commonly referred to as the return period of that earthquake. So, return period is important. Return period we already discussed, it is a simple term that after how many years an earthquake will be repeated. So, that is basically return period. When the logarithmic of the annual rate of accidents of Southern California earthquake are plotted against earthquake magnitude, a linear relationship was observed. So, we will discuss that relationship later in the form of graph, but in the form of an equation. So, this relationship is expressed here, lambda m is the manual annual rate of accidents of magnitude m. So, in this relation m is the magnitude of earthquake and lambda m is the rate of accidents annually. There are two parameters, one is A and another is B. Now, let us discuss about these parameters. If you have if I put magnitude 0, m equal to 0, then what will happen? Log lambda m will be A. For m equal to 0, if I put m equal to 0 in this equation, then lambda m equal to, you get it 10 to the power A, right. So, 10 A is the mean and yearly number of earthquakes of magnitude greater than or equal to 0 as written here, and what is B? Describe the relative likelihood of large and small earthquakes. What are the chances of likelihood? B will be applicable when m is not 0, because if B is if m equal to 0, B is does not have any meaning here. So, if you have some large or small magnitude earthquakes, so B describe the what are the chances of occurring of that earthquake. So, this relationship is further plotted here, but before that, as the B value increases, the number of large magnitude earthquake decreases compared to those of smaller. If you increase the B value, what will happen? Lambda m will B increases, lambda m will decrease, and lambda m is your annual rate of accidents, so that will decrease. So, when the B value increases, the number of large magnitude decreases compared to those of small magnitude. Now, this Gutenberg-Richter law is not restricted to the use of magnitude as a description of earthquake size. Epicentral intensity is also been used, and these A and B parameters are generally obtained by what we call the regression on a database of seismicity from the source zone of interest. So, we do the regression analysis, the database of seismicity regression analysis is done on the database of seismicity, and this seismicity should come from the source zone of interest. That is, source zone of interest means a zone near your site. This relationship which we have discussed is plotted in this graph like this, which is given by Gutenberg-Richter. So, what you have on x axis, you have magnitude, this is on the normal scale on x axis, while on y axis you have the log scale. In fact, this is if I say on the log scale, you can remove the log also. So, you have lambda m value in terms of log scale. So, ultimately and you have tan A, that means this intercept will be A here. Okay. When I put m equal to 0, magnitude equal to 0, then the value of lambda m is 10 to power A as given here, or value of log lambda m will be A. So, and B is the slope of this line, So, what you could see, as the magnitude increases, then your lambda m decreases. So, that means higher magnitude earthquake, like rate of recurrence will decrease. So, chances of the higher reoccurring of higher magnitude earthquake is less compared to smaller magnitude earthquake. Now, let us have one example on application of GRR law. Let us compute the return period of M8 earthquakes on the two belts, one is circumpacific and alpide belts. So, and this return period we need to compute for a magnitude of 8 earthquakes. So, this is given in the next slides. What you have in this slide? You have a GRR relationship, and this GRR relationship has been for two sides. First is alpide belt down and circumpacific belt. So, for 8 magnitude earthquake, if I draw, so this is my point here, which is about the value. If I read this value on, of course, it is on the log scale. So, it is about 1.76, while for alpide belt I have here this value, which is I think somewhere you have 0.31. So, this is 0.31. So, this value of lambda m is per year, that is the number of earthquake accidents which exceed a certain threshold limit. Here threshold limit we are putting is 8 magnitude of earthquake. So, what it says, in the circumfacic belt the chances are there 1.76 times the 8 magnitude will be exceeded, while in alpide belt it will be chances are 0.31. So, that means now if we determine the return period for both these like 8 magnitude of earthquake in these regions, then the return period TR, corresponding return period which is like said in the TR, this will be opposite of lambda m. So, 1 by lambda m. So, circumference chances are there that within 0.6 year, that means 0.6 into 12, so around 7.2 months. In 7.2 months it is chances that the 8 magnitude earthquake will repeat, while alpide belt it will take 3.2 years to repeat that 8 magnitude earthquake. So, that means seismicity of circumpacific is more than the alpide, which is obvious from this figure also. So, this was about application of GRR law. Now, the last part of this lecture, that is what we call temporal uncertainty. So, when we talk about temporal uncertainty, as I mentioned, this temporal here mean is related to time, it is not temporary, it is related to time here. To calculate the probability of various hazards occurring at a given time period, the distribution of earthquake occurrence with respect to time must be considered. So, what is the distribution of occurrence, chances of occurrence, and this should be done with respect to time. Earthquakes have long been assumed to occur randomly with time, and in fact, if we have examined the available seismicity records, that has revealed little evidence when aftershocks are removed of temporal patterns in earthquake occurrence. So, what has been observed, that if we remove this the data related to aftershocks, then we get that there is not much variation with respect to time, but that is why we need to consider the data of aftershocks also. So, we to get the temporal uncertainty. Now, continue with this. So, what is there? The assumption of random occurrence, that earthquake may occur randomly, it allows the use of simple probability model, but it is inconsistent with the implication of elastic rebound theory. So, the temporal occurrence of earthquake is most commonly described by a model called Poisson model. Poisson is the name of the person who invented this model, and it remains the most commonly used models for determination of PSHA, probabilistic seismic hazard analysis. So, in this case temporal uncertainty in the Poisson's model, it provides a simple framework. This model provides you a simple framework for evaluating probabilities of events that follow a Poisson's process, one that yields values of random variable which describe the number of occurrence of a particular event during it given time interval or in a specified spatial region. Since PHSA deal with temporal uncertainty, the spatial application of the Poisson's model may not be considered if you deal with the you consider the spatial spatially here, that means related to space again. So, that may not be if you are considering temporal uncertainty and if then again spatial uncertainty, that will complicate it for particularly for this model. So, this is done one by. Now, temporal uncertainty in case of Poisson's model, how it is dealt. For a Poisson's process the probability of a random variable, that is n, representing the number of occurrence of a particular event during a given time interval is probability. Here what is P? P is the probability, P stand capital P is here probability. What are the chances of probability? And probability, you know, the number is between you have this number, this is probability. This number P is stand between 1, P value could be between 0 to 1, that is 0 to 100%, and this is between capital N should N. What is mu here? Mu is the average number of occurrence of the event in that time interval. What are the chances? Average number of occurrence. So, with this we can find out the probability. The time between events in a Poisson's process can be shown to be exponentially distributed. So, like here. Now, the last part of this is accuracy of PSHA. What are the chances like accuracy of probabilistic seismic hazard analysis? The accuracy of PSHA depends on the accuracy with which uncertainty in earthquake size, location, recurrence and effects can be characterized. If you can characterize uncertainty in very good way, your model is going to be accurate. If accuracy cannot be quantified in a proper way, then model is expected that it may not be very accurate. All the models and procedures for characterization of uncertainty of these parameters are available, but they may be based on data which are collected over a period of time that geologically are very short. So, if you have a large span of data which is collected from many decades or let us say hundreds of years, then chances are that these models will be working well. So, always as a result engineering judgment must be applied for the interpretation of PSHA results. Now, perhaps you may ask one question, we talk about DSHA and PSHA. So, what we need to do? So, what NCSDP recommend particularly or insist rather for important project, that both DSHA and PSHA should be carried out, and once you carried out both DSHA and PSHA, whichever is given you the conservative result, that should be considered for the design. But sometime what happens we get more conservative values, then it need to be discussed again, because otherwise it may be difficult to design the structures for your dam, they may be very uneconomical. So, that is how the committee does for that. So, this is one of the expert area where you need to carry out both DSHA and PSHA. If you get the results, similar result from both the DSHA PSHA, fine. Now, if you get from the conservative approach, we will say we consider the worst case, however, then we need to see the economics also. So, with this, thank you very much for your kind attention.